astro-seminar. Happy New Year to all of you, and I hope you enjoy wonderful Christmas holidays. Today it's a pleasure to introduce our first speaker 2025, Blessing Musiimenta. Blessing earned her master's degree in physics in 2019 from the Barara University of Science and Technology in Uganda. Holidays. Today it's a pleasure to introduce our first speaker 2020. Sorry, the YouTube transmission. Her master's project involved leveraging multi-wavelength data and Fermi-Lat analysis to identify new gamma-ray blazars from infrared selective blazar candidates. Following her master's degree, she joined the prestigious Bid for Best Innovative Training Network as a Marie Curie Research Fellow. Bid for Best, which stands for Big Data Application for Black Hole Evolution Studies, is an advanced doctoral training program focused on one of the most cutting-edge areas of astrophysical research, the formation and evolution of supermassive black hole in galaxies. Blessing is preparing to defend her PhD thesis next month at the University of Bologna under the supervision of Professor Marcella Brusa, and she is currently working as a postdoctoral researcher at the Univ. Her research center on the connection between active galactic nuclei and their host galaxy at high redshift, contributing valuable insights into the coevolution of galaxies and black holes. Today, Blessing will present on the topic incidence and energetics of AGN winds in the distant universe. So thank you very much, Blessing. The floor is yours.
Okay. Thank you for introducing me. And thank you for introducing me and thank you for inviting me. So I'm going to talk about some of the works that I've been working on during my PhD and also during my postdoc position. And this work has been done in collaboration with some members from the eROSITA collaboration, then the Bid for Best, and also the HS team. So I will just begin with a brief introduction about active galactic nuclei or AGNs and galaxy evolution. So as of today, we know that most of the galaxies contain a supermassive black hole at their center. As shown in this image, I'm just showing the groundbreaking image of this black hole at the center of this AGN, which is quasar in this case, light quasar in this case. So these supermassive black holes, sometimes they go through an active accretion phase. And during this accretion phase, they can trigger star formation, black hole growth, and also they can ignite AGNs. So during this process, or during this AGN activity, they can drive an amount of material or gas into the surrounding interstellar medium. And this material can be in form of jets or winds, and or what we can call the AGN-driven outflows in this case. So these AGN-driven outflows can also regulate the accretion and also the ejection process. And this one should be like a reverse process. And in regulating, so they also provide feedback mechanisms to the host galaxy, thus having an impact on the galaxy evolution. So since I'm talking about AGN feedback, I'll talk more about this AGN feedback process. So this AGN feedback process is may happen in different episodes and also in very short phases, which in this, like as you can see in this sketch, which is from the evolutionary scenario depicted from Hopkins 2008, it is a very short phase compared to the AGN lifetime. And this evolutionary scenario is just showing the case of the merger, which is one of the processes that actually trigger black hole growth. So during this phase, it has been known that when this happens, the energy produced by these supermassive black holes can suppress star formation. However, this has evolved, and now both from observations and both observationally, theoretically, we have seen that this energy can both suppress star formation, like the negative feedback, which is shown in these simulations. And also it can also enhance star formation, which is the positive feedback, where we can see enhanced star formation by these outflows in these observations. So this AGN feedback, because of its effect on the galaxy evolution, it is really important for us. That's why we care about it. And there are already key observational evidences that show that highlight the importance of this AGN feedback. One, which is the tight correlation, the local tight correlation between the mass of the black hole and the galaxy properties, such as the velocity dispersion or the bulge mass. So this tight correlation, what it tells us that these two actually brought together so they can affect each other. Also, the simulations, they have highlighted the importance of AGN feedback in regulating the black hole growth and star formation, therefore determining this steep slope in the mass function of galaxies at the high mass end, which means that in a simulation without AGN feedback, simulations cannot produce some of the observed properties. These also actually include the morphologies, the colors, and all other properties, most of them, like all other properties. Since it is important to study this AGN feedback for us to understand the galaxy evolution, but also this AGN feedback is complex. For example, it is really challenging to detect these outflows because as I'm showing in this cartoon, which is from the review by Harrison and Ramos Elmelda 2024, these outflows can be observed at different scales, parsec scales like or the nuclear scales for the disk winds, or the galactic scales up to megaparsecs. So since we observe these outflows at the different scales, it is challenging if we want to compare with other properties, for example, with a star formation rate, which is actually derived from a larger scale. So these outflows also have multi-phase, which means they can be observed in atomic and molecular phase, or warm ionized and hot ionized. And these different phases, they can be detected using different emission and absorption lines, which are observed in different wavelengths. For example, the highly ionized gas in the X-rays, then the neutral molecular or atomic in the millimeter and radio, and then the ionized in the optical. So it is challenging to obtain observations in these different wavelengths for the same sources for us to make like informed conclusions about the effect of these outflows on their host galaxies. So it is a bit challenging, although there have been studies that have been looking at the multi-phase outflows. And there is some improvement in this case. But in this study, I'm going to only be focusing on the ionized phase. So because, like I said before, because this blowout phase is short, so the sources are rare, we need large area sky surveys to select these sources. And then we also need innovative selection methods and dedicated observations for us to also perform both individual detailed source analysis, also the using for statistically large samples. That's why we need innovative selection methods, large area sky surveys, and dedicated observations. So in my studies, since we don't, there are actually no like unique features or unique properties that can be used to select these kind of sources if we need statistically large samples or to cover different AGN populations. Since we do not have these unique features in our study, we use the properties of AGN with outflows that we know from theoretical models to select these sources. In this cartoon, I'm just showing the blowout phase, which is also from Hopkins 2008, where in the blowout phase we expect this AGN to be luminous, So they are also obscured, which means we can use the moderate Coulomb densities to select these sources. Then they are also within the dusty shaded environment, so we can observe them with red colors, which means they are luminous in the X-rays and the infrared, then faint in the optical. They're also accreting close to the Eddington limit, so we can also use the Eddington ratio to select these kind of sources. So with this, my goal for these studies was to actually develop an approach that can isolate these red obscured and high accreting quasars at redshift 0.5 to 3. Then I searched for the presence of ionized outflows and assess the effect of these AGN outflows on their host galaxies by comparing with simulations. So in my studies, I've been using the eROSITA X-ray surveys. Most importantly, the eFEDS survey, which I used in the first paper that I will show you. The eFEDS survey, which was taken within the 4 days of deep observations of the eROSITA from this small region, like approximately 140 square degrees. And this survey was important for this study because it is very rich in both photometric and spectroscopic wavelength coverage. So there are many follow-ups in this field. Then I also used the eROSITA all sky survey, which is the eROS. So in the first paper, which is Musiimenta 2023, what we did, we used these colors, like I said, to select red sources, we used different colors like the R-W1, then the I-W3, the I-W3, I-W4 here, then I-W3 here, and then the flux ratios, which is the X-ray to optical flux ratios. And in that case, we are selecting sources that appear in this region, which are the radar sources in these diagnostics. Then, since we know that they also have like moderate Coulomb density and also accreting close to the Eddington limit, we selected sources that appear in this forbidden region here, which are supposed to be associated with outflows. So with these 5 methods, we selected 1,400 candidates. So among these 1,400 candidates, there is only one source which was actually selected by all the methods. And I'm going to talk about this source later. We did a Muse follow-up for this source. Yeah, I'll talk about it later. And then we also went ahead to do X-shooter follow-up for 10 of the sources at redshift 1 from these 1,400. So to trace ionized outflows from these 1,400 sources, we use the SDSS spectra. But in this case, since we are considering only since we are interested, of course, in the ionized outflows, we could only trace these outflows in let's say 80 sources, which were at redshift 0.5 and 1, where we can observe the O3. But also, we were also limited by the quality of the spectra from the SDSS, so we could only do this for 50 of these sources. So with this, to trace the outflows, we fit the spectra with 2 components, where the green, which is the narrow component that is supposed to be tracing the ordinary gas motions, then the broad component, which is associated to the outflow. So with this, to tell whether you have an outflow or not, is looking at the asymmetry of the line profiles, and also if they are asymmetric, and also looking at if they are redshifted or blue shifted in this case. So with this, we actually found that 23 out of 50 of these sources, they have outflows. And this is when we considered those ones with high significance. So if we were not very conservative about that, our sample would have gone as much as 80%. And this tells us that our methods in isolating these kind of sources actually are good in it confirms that our methods are actually doing good in isolating these kind of candidates that are expected to be in the outflowing phase. So with this, then I looked at the correlation between the AGN properties, which is the AGN bolometric luminosity here, and the outflow properties, which is the outflow velocity, in this case, the Vmax, the maximum velocity. So with this, in the previous studies, it has been found that these two properties actually correlate. So the velocity depends on the AGN bolometric luminosity. But in our study, actually, we found that there is actually weak or no correlation between these two properties. You can see the red stars are sources from our study. And what this means is that since our sources were actually selected to be X-ray light, it means that this extractive phase may be a best trace of the fastest phase of winds, and also the velocity does not necessarily depend on the AGN bolometric luminosity. Again, this also points to the importance of the sample selection because, yeah, like I said, these sources are completely selected differently from the literature compilation. So also we went ahead to look at the mass outflow rate and the AGN bolometric luminosity. So to do that, of course, we determine the outflow mass, which depends on the luminosity, the O3 luminosity, and the gas electron density. Then the mass outflow rate, that depends on the velocity, then the radius of the outflow and the mass outflow rate, and the mass of the outflow. So from this, we actually find that of course, we compute the kinetic coupling efficiencies. This is one way to tell whether these outflows have an effect on their host galaxies, where we compare the efficiencies with the theoretical predictions. So we find the efficiencies between 1 and 10 in 30% of our sample. And what this means that these outflows are very relevant from the energetic point of view, and they could have an effect on their host galaxies. So what I did mention is that this although we find a correlation between these two properties, there is a large scatter, but the large scatter was already explained, of course, in almost model 2022, which means that the mass outflow rate may not only depend on the AGN bolometric luminosity, but also on the coupling between, let's say, the outflow and the ISM, or the amount of gas in the ISM, different factors. So, like I said, we did a follow-up study for one of the sources, which is a red obscured quasar at redshift 0.6 using the Muse instrument. And with this, here I'm just showing the HSC image of this source. And you can see that it is a red source, clearly from here. And then it also appears to be like merging. Oh, we don't know. Then also we found that it has outflows using the SDSS spectra shown here. So we obtained observation to explore the IFE observation to explore the environment around this source. Then also see if this quasar is located in a merging system or not. And then since of course, the SDSS spectra, we have, of course, more assumptions in that there are some of the outflow parameters we cannot measure with that. We also wanted to obtain more accurate measurements of the outflow properties. So this is the Muse data cube of this source. And when you look at this is the O3 flux map that is shown here. When you look at the O3 flux map, it appeared it looks like a goldfish galaxy. So we named this quasar as the goldfish galaxy. So in order to look at the environment, the companion galaxies around this source and also the gas distributions, we obtained different velocity. We considered different velocity beams and then looked at the different structures. And from here, you can see this is the systemic, then you go to the blue and then the red. And you can see that within different velocity beams, we can see different structures. In particular, you can see that there is an extended structure in the southwest region. So if you also look at the RGB image of the source in the southwest region, we kind of see that there could be like a kind of rotation that is going on within this extended structure. So we increased the field of view of our data cube, and we looked at the different emitting sources in this field of view. So we measured the redshift of these sources, and we found that 3 of these sources, they have the redshift that is similar to our quasar, which means they are companion galaxies. They are shown here in yellow stars. And this one just showing the continuum, then the H beta, and then the O3. So with this extended structure, I'm not sure if it is very clear here in red, the O3 here in red. With this extended structure, anyway, you can see it here in the RGB image. With this extended structure that is actually moving towards the companion galaxy 3, and the fact that we saw that it may be having like a rotation that is going on, we conclude that that our source is actually could be in an interacting system, possibly merging with other 3 galaxies. So I went ahead to perform the spectral fitting of this source for, of course, for spaxel by spaxel fitting. And this is the model flux from the fitting. And in this case, I used the multiple component fitting compared to what I explained before. In this case, I used the multiple component fitting. So this is the model flux. Then this is the velocity peak. Well, we don't actually see any rotation there. And then this is the 5 percentile velocity. This is supposed to test the negative velocities. Then 95 percentile velocity for the positive velocities. And then the line width. The line width is an approximation of the velocity dispersion that tells you how disturbed the gas is. And then this is the number of Gaussians in each spaxel. So from this, we see that in regions where we see high velocities, we also see high velocity dispersion, and which means there is a disturbed gas, so we associate this to the outflows. So from this, of course, we use the same formula that I showed before and measure the mass outflow rate, the kinetic power, and then the kinetic coupling efficiency. And in this source, we find that the kinetic coupling efficiencies are between 0.1 and 0.2. Comparing to theoretical prediction, these are low, which means these outflows are not relevant from the energetic point of view, or they may not have significant impact on the host galaxy. But also keep in mind that this is just an ionized phase. We're just considering one phase. And if from the literature, it has been shown that the molecular phase actually carries more mass outflow rates than the ionized phase. So I think looking at maybe the molecular phase of this source, we would find that maybe it is carrying more mass outflow rates in that case, and maybe could have an effect on the host galaxy. So with one phase, of course, it is complicated to tell whether the outflow has an effect on the host galaxy or not. It is hard to conclude that. So with this, we also find that we find a mass loading factor of 5. What this mass loading factor, that is the mass outflow rate over star formation rate. So what this means is that this outflow may play a vital role in the AGN feedback, and actually could potentially be driving like more gas more like faster than the star formation, meaning this can also be like AGN-driven winds, AGN-driven outflows than the star formation-driven outflows. Okay, so in the next project, which I'm actually working on right now, here we try to select AGN in feedback phase, again from eROSITA, but in this case, we apply machine learning. Just to give a recap of what we did in Musiimenta 23, in the first paper, we use the different methods that use colors to select, then the column density and Eddington ratio to select sources that are expected to be in the feedback phase. And within, also shown in the Venn diagram, and within these sources, we found that 45% of these sources actually show outflows, which was confirming that these methods are actually performing well in isolating these kind of sources. But also, we were limited by the spectroscopic redshift sample, which was very small, and meaning it was not an accurate representation of the full outflow candidate population. And also, when we populate these different diagnostics with the different samples that we obtain with our traditional methods, we see that these sources don't appear to occupy like a unique region. They don't have like unique features that we can use to actually select these sources. So this could lead to low reliability and completeness. So we could, with this method, we could be also losing like potential candidates. And this, when you want to apply this on large samples, this could be time-consuming and inefficient. So our reason to include machine learning in these methods is to improve these challenges, improve the completeness, the efficiency, maybe also identify more features that we can use to select these kind of sources, the sources that are expected to be in the feedback phase. Okay, then, so to do this, we got our training and testing sample from the eFEDS catalog. And to do that, of course, I performed the optical spectral fitting using the SDSS, like I explained before. And with this, I compiled two samples, one which is the AGN in feedback phase. So sources that are confirmed to have outflows, that was 368. Then AGN not in the feedback phase. And those are 146. So with this sample, I applied different classification algorithms that are shown here, the random forest, the logistics regression, the decision tree, adaptive boost, and then gradient boosting, and then the voting classifier that includes all these, and then one neural network classifier. And with these classifiers and the data, I used different features. These features include the column density, Eddington ratio, and the bolometric luminosity, which are some of the features that we used in our first paper, and some colors. But also we add more features. We add more colors using different magnitude combinations here from the optical and the wise. So with this, to train our models, we consider different scenarios. So the first scenario, we use all the features where we remove the redshift. Then the second scenario, we use all features and keep the redshift. Then in the third scenario, we further select our sample using our traditional methods. Then we use only the color features without the luminosities, without the luminosities, the Eddington ratio, and so forth. And then we go the redshift. Then scenario 4, we also do further selection on the sample using our traditional methods. Then we exclude some of the properties like the column density and Eddington ratio, because we wanted to compare with the sample that can be selected by the traditional methods, and some of these properties are not available in the sample where we shall be applying our models. So with this, we find that actually scenario 3 is the one that is performing better with the random forest classifier with accuracy of 95%. We are showing it here in the confusion matrix, and also in the matrix that is showing different metrics from the different classifiers that we used. And this is the random forest classifier. So After this, we applied this random forest classifier to the eROSITA all-sky survey, the first eROSITA all-sky survey, which is the eROS1 that has more sources compared to the eFEDS that we used before. And we just eliminate, of course, sources that have missing values in the features that we shall be using. So we remain with approximately 99,000 sources. So with this, we apply our random forest classifier. And in the same scenario, that was performing better. So this random forest classifies approximately 29,000 sources as those in the feedback phase, then 70,000 sources as those not in the feedback phase. And in this diagnosis, these are some of the diagnostics that we used in our first paper. So I just populate these classified samples, and also the sample that would be selected if we used our traditional methods. And from this, actually, we can see that this machine learning is classifying 30% of the sources as feedback phase, compared to the 10% that we isolated in our first paper in the eFEDS. But this can be attributed to the samples. First of all, the eROS1 is more luminous than the eFEDS, so which means we expect more feedback in this sample compared to the eFEDS. And also from here, if you look at the numbers here, you can see that the machine learning methods are isolating a very larger sample as feedback phase compared to the traditional methods. So we are improving the statistics of the AGN expected to be in the feedback phase, which is really important for us to explore this AGN feedback. So to actually see whether these sources which were classified as feedback phase are actually in the feedback phase, we had to perform spectral fitting for these sources. And to do this, of course, we use the SDSS spectra, and again, we are limited by the quality of the SDSS spectra, which was not very good. So only 484 sources here had good quality spectra, where in the non-feedback phase, only 2,968 sources had good quality spectra. So with this, we find that 316 sources have actual outflows in the sources that were classified as feedback phase. That is 65%. And then in the non-feedback phase, in the sources that are classified by the machine learning as non-feedback phase, also found that 61% of these sources have outflows. What this means is that we are still losing potential candidates. If we use the machine learning, we are still losing the potential candidates that could actually have outflows. But also, if we compare with the traditional methods that we applied in our first paper, if we apply these methods in the eROS1, as you can see, we have 52% of these sources as outflows. Those are just 13. So still we are improving on the selection method. Although we may lose potential candidates, but we are improving on our selection methods. And this is still under progress, so but maybe improved or not. I don't know. It depends on the sample. Need to improve the sample. So the takeaway message and the summary is that from our first paper, eROSITA it shows that the eROSITA is a powerful discovery machine for AGN in the feedback phase, and we find a weak or no correlation between the outflow velocity and the bolometric luminosity, which highlighted the importance of the sample selection in these kind of studies. And then the extractive phase, also the obscured is a best trace of the first test phase of winds. So in the second paper, here I'm just showing the cartoon, which is the conclusion from our analysis, where this is our quasar here. and then this companion galaxy 1 and this companion galaxy 2. And then this extended emission in the southwest region is just an ionized cloud that is due to the interaction that may be going on between our quasar and this other companion galaxy 3. And then we also find that the outflows in this source are likely AGN-driven than star formation-driven, though they are less significant from the energetic point of view, but also considering that this is just analysis of the single phase, not all the phases. And then for the machine learning selection methods, we found the random forest classifier performs better, and also machine learning is identifying a large sample of AGN feedback phase compared to our traditional methods, but this is still this is still in progress. And thank you for listening.
Thank you very much, Blessing. Very interesting results. So we have time for questions. You can unmute your microphone and ask the question if you want. Well, in the meanwhile, I have a couple of questions. And for example, I was wondering if for the within your sample, which show ionized outflow, do you also have any information about the molecular emission, if they have any molecular outflow?
So I haven't explored if they have any molecular outflow, but the from the first sample, actually one of there are 1,400 candidates isolated to be in the feedback phase. Almost 1/6 of them have like LOFA data, but this is not explored in this study, but supposed to be like the extension of this work. Some of the work that I actually plan to do to explore the radio part of this source, yeah.
And I was wondering if you can derive, for example, the momentum rate of the ionized phase to see if they are momentum-driven or energy-driven outflow. If you have
on the ionized phase.
Yes.
We did that in the I beg your pardon for the question. I beg your pardon.
Sorry, if you derive the momentum rate of the ionized phase of your sample.
Yeah, we derive the momentum rates, the momentum rate for all our sample, and we find that for the first paper we find that these outflows are actually like more radiation driven than they are more radiation pressure driven outflows. Also energy driven than momentum driven.
Nice. And a few questions about the last galaxy at redshift 0.6. Maybe I missed it. How do you identify the three companion? Can you see the emission, the oxygen 3? Or how do you identify the companion around your quasar?
So to identify the companion, I obtain the spectra of these sources, the optical spectra, and then measure the redshift of these sources using different emission and absorption lines. So if they have the same redshift as our source, then we consider them as companion galaxies.
And the extension of the outflow of the quasar with respect to the host galaxy is extended or is compact? Because I was looking at the map, but I couldn't see very well the extension, the kinematic maps you showed before.
Okay, I can also go to the kinematic maps.
And the previous one is one.
The previous one?
No, the other one.
Yeah, so here we are not showing okay. We cannot see the companion galaxy 3 here. It is just this way. But this outflow is extended. It is like 9 kiloparsec, close to 10 kiloparsec. So it is an extended outflow compared to the companion galaxies. Yes.
Very extended, yes.
It is very extended, and yeah.
And here on the number of Gaussian, you picked up to 6 Gaussian, I see, in the inner region.
Yes.
You are including the doublet, the oxygen doublet, or they are 6 independent components?
These are for the doublet. They are 6 independent, but we do for the doublet, yes. But of course, we obtain the total line profile of only the 5007 angstrom. So we don't analyze to obtain the outflow properties. We don't analyze the other doublet. We only analyze for the O3 at 5007. But for the fitting, we do both.
Okay.
Yeah.
Any other questions? Let's see on YouTube.
Can I ask something? Do you hear me?
Yes.
Okay, so yeah, it's in line with the question made by Enrica before. So with this new selection method that now selects many more sources, maybe it would be interesting to look for their indications of outflows at different scales. So, for example, molecular emission or radio, as you mentioned, outflows, and also broad absorption lines. I don't know if you have. You should have probably in your redshift range. You mentioned it was between 0.5 and 3. Is it correct?
Yes, 0.5 to 3.
Okay, so you should have the magnesium 2 line, and then you should maybe have some absorption lines also there in the broad absorption lines associated to magnesium 2. That maybe you are now more likely to select with this new selection method.
New selection method. Yes. Exactly. Like, okay. Thank you for the suggestion. So for the first sample, yes, we select from 0.5 to 3, but then we only use the O3, which is from 0.5 to 1. So a lot of sources at redshift greater than 1, those ones are left out. And also, yeah, so in this study, we really don't do follow-up for most of these sources, but the plan is to do follow-up for all the sources in the first selection method, and also this machine learning method, all of them from eROSITA, to look at both the radio and also those ones at redshift greater than 4. We can also look at the carbon 4 and so forth. Yeah.
Okay, thank you.
Yeah. Okay.
Any other questions? Well, if not, let's thank Blessing again. Thank you very much, Blessing. And thank you very much to all for joining us.
Thank you for inviting me.
Thank you. It's a pleasure. Bye, everyone. Thank you.
Bye.
Bye.